and we're going to start off with a review of long division. Some of you have probably not done long division since middle school. Some of you have completely blocked out middle school altogether and can't remember it at all. Some of you might have learned a different technique. But I'm going to start off by giving you a review of what long division was most likely taught in middle school, and then also give you a little bit more explanation, because sometimes when you're taught a technique in middle school, you remember the technique but have no idea why you are doing it. So what did long division look like? Well, you would start off by writing the 2748 inside something that kind of looks like a square root but isn't a square root sign, and writing the 13 outside. Just a show of hands, how many people recall that they've seen this before, even if they don't remember how to do it? Okay. All right. How many people did long division with a different technique? All right. Okay. So we'll do this first and get an idea. What the idea of long division was your teacher said, go from the left-hand side of the big number and then look until you get a number that you can fit 13s into. So for example, you couldn't just do 2, but if you went to 27, you could fit 13s into 27. How many 13s fit into 27 without going over 27 would be 2. And you were told to write the 2 over top of the 7. Then 2 times 13 is 26. And your teacher told you to subtract. So this was the method, but now we're going to take it back a little bit and explain a little bit more. What is this actually doing? Okay? When you were looking at the 27, really, this isn't 27, this is 2,700. And we're temporarily forgetting about the 48. So we're just looking at 2,700, and when we're asking how many 13s go into 27, you're actually asking how many 13s go into 2,700. But that's hard mental math. 13s into 27 is a lot easier to think about. And so when we write this 2, that 2 is in the hundreds column. That 2 is really 200. And if I did 200 times 13, I would get 2,600, which is really what you have there. But to make it easier for middle school students, you're not thinking about 2,700 because that would blow their minds because the number is so big. We just kept it at 27, but sometimes we lost a little bit of the understanding of what's going on. Now, if you had 213s, well, that would get you 2,600, which isn't quite to 2748. We subtract to say, you're really off by 148. And now we would repeat this process and say, well, now I have 148. How many 13s are there in 14? There's 1. So we would write a 1. 1 times 13 is 13, but that 1 is in the tens column, which really means it's a 10. And 10 times 13 is really 130. And so when I do 10 13ths, I get close to 148, as close as I could. And when I subtract, I'm left with 18. Now I look at the 18 and say how many 13s are 18. There's 1 of them. Subtract that. And we get a remainder of 5. So really what long division is saying, first we're looking at our big numbers, then we keep going down and slowly making it work until we get an answer that's close. And what we have as a result here is we can write out the following. We know that 2,748 is equal to 13 times 211, but it's not quite right. 13 times 211 is close, but there's a remainder of 5. If you look at multiplying these, you will see that 13 times 211 is 2,743. That remainder of 5 says you would have to add 5 to make it work. We were close. We got as close as possible, but we were off by 5. And this is what is a statement that's true. We could also write this as a division that 2,748 divided by 13 is equal to 211, but there would still be 5 left that still needs to be divided by 13. So as an exact answer, the answer to this is 211 and 5/13 as an actual perfect answer. Now, why is long division not used that much? Well, you have calculators. So it's pretty easy to type these numbers into your calculator and get the answer right away. Sort of makes you feel like, well, why would I go about doing this long division? We're going to find out, though, that this technique is also going to be used in algebra, where we can't type things into our calculator. So we're going to see that as well. Let's try the other one just to practice. So we have 4,212 divided by 27. And the same idea, we start from the biggest numbers and we go, okay, when can I get a 27 into something? I'd have to go to 42. How many 27s fit into 42? Only one. 2 would be too many. Which would get me 27. I subtract that. Really, that 1 is in the hundreds column. And really, that 100 times 27 is 2,700. When I subtract, I'm left with 15, but I'd also have the 1 and the 2 come down. We'd be left with 1,512. Now, same thing. We'll do the same color coding that I've been doing. There's no 27s and 15, so I'd have to go to 151. How many 27s fit into 151? This is a little bit more mental math than you probably want to do this morning. 5 times 20 is 100. 5 times 7 is 35. So this will be 135. Really, that 5 is a 50, so subtract this, then we are left with 162. Now we have to look how many 27s are 162. It ends up being 6. And it works out perfectly to have no remainder. So when things have no remainder, we know that this works out perfectly, that 4,212 is exactly 27 times 156. So the idea of long division is to figure out what's the biggest number you can make that works, subtract to see how much you have left, do that process again. Do you notice that we're doing the same steps again and again and again until we finish? It's sort of sometimes what's called an algorithm, where you do something, get a result, do that, do it again, get another result, and keep repeating that process until you're finished. So other long division techniques, what, someone who did something different. How did you learn long division?
We learned to write it different, so we go to equation, understand,
So, okay, let's take the first one you had, 2, 7, 4, 8, and 13, okay? So this is the one we're going to do.
yeah, and then we did equals 13.
So you,
13 equals, yeah, and then we did the same thing.
yeah,
So we wrote down 26 underneath the 27.
okay, like this.
Yeah, or like, okay, 26.
Just
put
one.
this 2 times, so we put in the 2 at the end of the equal sign.
You just put it on the other side of the equation.
It just looks like
It's the same idea, but with just looked a little bit. Okay. I've also seen, sometimes I've seen it like this, where they start with the 2748, and then you just say, okay, how many 13s do you want to take off? What kind of mental math? Doesn't matter if it's the closest or not. Let's say you want to take off 100 13s. 100 13s is 1,300. Well, that would leave me with 1448. I could take off another 100 13s. That would leave me with 148. Now I could take off 10. That's 130. That would leave me with 18. 19. Oh, I can take off one more. And add this up and I get 211. And I get 5. And this technique doesn't mean you have to get the right answer right away, but you just have to find something. Whatever your mental math you feel you could do. You could do the tens a whole bunch of times if you wanted and keep subtracting 130s. It would just take you longer, but it wouldn't be wrong. So I've seen that technique as well. Now what we're going to look at is how does this work with algebra? The setup is going to start the same. We want to divide 3x squared minus 4x plus 5 by x minus 2. So we're going to set up our long division. 3x squared minus 4x plus 5. We're dividing by x minus 2, so we're going to write that x minus 2 out in front. And just like long division, we're going to look at the biggest number inside the division sign, which is the 3x squared. And we're going to ask ourselves, is it possible to get close to 3x squared by multiplying x minus 2 by something? In fact, I can get an exact 3x squared if I multiply the x minus 2 by 3x. Can you see that I would get a 3x squared? So what I do is above my x columns, I write 3x, and I multiply that 3x times the x minus 2, just the same way that you multiplied the 2 times the 13. So 3x times the x would give me 3x squared, and the 3x times the minus 2 is minus 6x. And if we think about what did we do next in long division, we subtract. But one extra step you have to do in algebra is you have to put brackets around this because you're going to subtract all of it. And when I subtract all of it, the 3x squared minus the 3x squared, that will be 0. Perfect. Minus 4x minus a negative 6x will give me plus 2x. And then the 5 minus nothing will still be 5. And now we repeat the process over and over again. Now what am I left with as my biggest number? My biggest number is a 2x. What could I multiply x minus 2 by to get a 2x? I'd have to multiply by a plus 2. 2, same thing, this then gets multiplied by the x minus 2. 2 times x is 2x. And 2 times the minus 2 is minus 4. Put it in brackets and subtract. This will be 0. 5 minus a negative 4 is plus 9. That's my remainder. So I can write out as a result that 3x squared minus 4x plus 5 is equal to x minus 2 times by 3x plus 2 If you multiply that out, it won't work out perfectly. I hope you can see you'll get a 3x squared. If you do the outside and the inside, you will get the minus 4x. But if you do the last ones, you will get minus 4 and not plus 5. That's where our remainder comes in. In order to make this work, we'd have to add 9, because it doesn't work out perfectly. It's close. When you multiply that out, everything's close, but you're off by 9. So we have a remainder. But now, we are able to rewrite 3x squared minus 4x plus 5 as two things multiplied together with a small remainder. We're going to do the second one together. Same color coding, so I started with blue. Now I'm going to have 2x cubed minus x squared minus 2x plus 1 divided by x plus 1. Same idea. You look at your first term and say, is there something I could multiply my x plus 1 by to get a 2x cubed? Okay. And the answer is 2x squared. So we write that 2x squared. So there's some formatting things. We make sure we write that 2x squared over the x squared, sort of have a column for each of our numbers. And then 2x squared gets multiplied by the x plus 1, giving me 2x cubed plus 2x squared. Put that in brackets and subtract. This will be 0. Minus x squared minus 2x squared will be minus 3x squared. And we still have minus 2x and plus 1. And now we just repeat this process. Our new first term is minus 3x squared. We ask ourselves, what could we multiply x plus 1 by to get minus 3x squared? Minus 3x. And again, that's written over my x column. Minus 3x times x is minus 3x squared. Minus 3x times a positive 1 is minus 3x. Put it in brackets and subtract. The number one mistake in long division is making errors with subtraction. Because here, like, this part is easy. This minus 3 minus this will be 0. But minus 2 minus a negative, this is going to be positive x. And then 1 minus nothing is still plus 1. Now we look at the x plus 1. What would I have to multiply x by to get x? I'd have to multiply by a plus 1. And when I multiply, I get x plus 1, put that in brackets and subtract. There is no remainder. And our fun is just about to start. I don't know if you realize how crazy this remainder of 0 is. But if I write out what this means that 2x cubed minus x squared minus 2x plus 1 is equal to x plus 1 times by 2x squared minus 3x plus 1 with no remainder, so I could write plus 0 or I could just leave it. And this, well, at least to me, this is super exciting because what you have done that you've never done in your entire life before is you have just factored an x cubed equation. Right? You know how to factor x squareds. You know how to pull out a factor of a common factor. But now, and we could even go further on this one if we wanted to. We could say this is equal to x plus 1. This is a quadratic, which you know how to factor. To get 2x squared would have to be 2x and x. To get the 1 would have to be 1 and 1. To get a minus 3, the outside and the inside, they both have to be negative. And now we have factored this completely. And what does that mean? You can solve, like, if this was an equation, when is this equal to 0? You now know it's equal to 0. Minus 1 plus a half and a plus 1. This is going to be very powerful in a lot of ways. So our technique of long division might give us a way of factoring something we haven't been able to factor yet. Now, long division here, this is something you can't do on your calculator. So knowing the techniques from regular numbers helps us with our algebra. Even though the regular long division, when you probably first learned it, you're like, why can't we just use a calculator? Why would I want to do all this work when I have technology that just tells me the answer right away? But here we get to algebra, which you can't type into your calculator. Oh, but there's another program. I know. There's always something that'll figure out everything for you. But it shows you where we can use this to solve. So if we look in a textbook, the textbook has explained it on the next page. Long division, what do? You write it out. You first look at what you need to multiply to get that x squared. You multiply it out. Then you subtract. Then you look at the next number. You multiply it out and subtract. And you finally get the remainder. So we call the answer to a division statement, we call a quotient. And the remainder, we call a remainder. And so when we go to example 1 here, and what I'm going to do for example 1 is get you to write up the following, because sometimes if you set up your long division incorrectly, you will run into problems. And the setup for long division with polynomials has some things that never came up with regular numbers. So there's two things for the setup. Number one, the polynomial needs to be written in descending order by degree. In other words, can you see that this is an x cubed polynomial? The highest one is an x cubed. What should come next if you were writing it in the proper order? The x squared. Is it wrong when it's written in the wrong order? No. But there is a proper order to write a number. Whereas regular numbers, there are wrong ways. If I want to write 482, I can't just decide, yeah, 482. You wrote them, oh no, this is how I write 482. I always write my hundreds here, my tens here, my ones at the beginning, because I like that. Oh, I could mess up elementary kids. Yeah, you can write whatever number you want, any order, yeah, it's okay. I get it. No, right? Works with 11. This is my ones, this is my tens. Okay. No, regular numbers, you can't do that, because the order really matters. But with polynomials, it doesn't matter that the 5 is there. It could be at the end, it could be at the beginning. But for long division, we're going to want to have it set up in the proper order to make our life easier. Okay? Second thing for the setup, we are going to need to add zeros if a degree is missing. This doesn't come up in our first one, because do you see that you have an x cubed? Then 1 less than x cubed, we have an x squared. Then 1 less than x squared is the x, we have that. And then 1 less than x is a constant. There's nothing missing in this polynomial. But sometimes you might get an x cubed equation that has no x squared. Then we're going to need to add a 0. So what I'm going to do for this right now, I'm just going to shrink it down just a little bit smaller, copy it, and paste it into our second example, because we're going to use it again in our second example. But now we have our setup ready to go. So the things we need to check for our setup. I'm going to write our polynomial inside of here. And we do have to change this one into the right order. So we would have the 3x squared next, then the minus 2x, and finally the plus 5. We're dividing by x minus 1. That would go out in front. So we look at our biggest term, the 2x cubed. And we ask ourselves, what would I need to multiply to get that 2x cubed? That would be a 2x squared. I write that 2x squared over my x squared column. Then 2x squared times x is 2x cubed, and 2x squared times the minus 1 is minus 2x squared. I put that in brackets and I subtract. This will be 0. 3 minus a negative 2 is plus 5. And now we just repeat this process over and over again until we've got a remainder. So I'm going to give you a head start. I'm going to underline that in purple. So there's finished up. I find that the biggest place where, if you're gonna make a mistake subtracting, it seems to be in the very last step. You're so excited to finish that you have people that write 5 minus 3, they'll write 2, because they're like, this is the last part, it's so easy, but you have to remember, you're subtracting the whole thing, so that negative gets distributed, and you'll get a remainder of 8. So now if we write out, what does this mean? We can write out that we've now figured out that 2x cubed plus 3x squared minus 2x plus 5 is equal to x minus 1 times by 2x squared plus 5x plus 3, but that doesn't work out perfectly. It's not a perfect factor. There is a remainder. In fact, if you multiply this out, you will get the 2x cubed perfectly. You will get a 3x squared perfectly. You will get the minus 2x, but unfortunately, you'll get minus 3 instead of plus 5. So to make it work, we have to add the remainder to this side, and then they will be equal. I'd like you to circle question 3b. No, not 3b. Sorry. Wrong numbers. That's for your second one. I'd like you to circle 3, everything but b, 3, A, C, D.